What if everything you see around you, the stars, the planets, even the air you breathe, started as nothing more than a whisper in the void? Picture the universe in its very first moments, a seething ocean of energy so dense, so unimaginably hot, that the rules of reality, as we know them, hadn't even been written yet. This is where our story begins, not with planets or galaxies, but with something far smaller, far stranger, the very first particles, the building blocks of existence itself. Scientists call this the Planck epoch, a time so brief it's almost incomprehensible, just 10 to the power of negative 43 seconds after the Big Bang. And yet, in that fleeting instant, the seeds of everything were planted. But here's the thing, no one was there to witness it. No cameras, no telescopes, not even light as we know it existed yet. So how do we unravel this cosmic mystery? How do we piece together what happened when time itself was still taking its first shaky steps? That's where the theories come in, bold, brilliant, sometimes downright bizarre ideas dreamed up by the finest minds in physics. Some suggest the first particles were primordial strings vibrating in hidden dimensions. Others argue for a frothing quantum foam where particles blinked in and out of existence faster than a thought. And then there are the wild cards theories that challenge everything we think we know about matter, energy, even the nature of space and time. Over the next 30 theories, we're going to dive into these ideas headfirst. We'll explore how a single speck of energy could have sparked the entire universe, why some scientists believe there might have been multiple Big Bangs, and whether the particles we take for granted today are just echoes of something far more exotic. This isn't just a journey through science, it's a detective story on the grandest scale, one that takes us to the edge of human understanding and dares us to peer into the unknown. So buckle up, by the time we're done, you'll never look at the night sky or the world around you the same way again. Imagine standing at the edge of absolute nothingness, no space, no time, no matter, just pure emptiness stretching endlessly in every direction. Yet somehow, from this void, everything we know came into being. That's the mind-bending premise of our first theory, quantum fluctuations in the void. At the heart of this idea is a principle from quantum physics, the notion that even in a perfect vacuum, particles can spontaneously appear and vanish in the blink of an eye. Think of it like a calm ocean surface suddenly rippling with tiny waves, except here, the waves are particles and antiparticles dancing into existence before annihilating each other. These fleeting disturbances, called quantum fluctuations, aren't just mathematical quirks they've been observed in lab experiments. But what if, in the universe's earliest moments, some of these fluctuations didn't cancel out? This is where something from nothing gets real. In the extreme conditions right after the Big Bang, the energy density of space was so intense that quantum fluctuations could have stretched far beyond their usual microscopic scale. Some theorists propose that one of these random blips, a tiny imbalance between matter and antimatter, might have snowballed into the first stable particles. It's like a single spark igniting an entire wildfire, except the spark was a quantum hiccup and the wildfire became galaxies. The beauty of this theory is how it bridges ancient philosophy with cutting-edge science. The Greek philosopher Parmenides once argued that nothing could come from nothing, yet quantum field theory tells us that the void is anything but empty. Empty space, it turns out, is a seething network of potential where particles borrow energy from the universe just long enough to exist. And if that borrowed energy never gets repaid, well, that might be how our universe got its first building blocks. Critics argue this still leaves the biggest question unanswered. Where did the void itself come from? But supporters counter that even a true vacuum isn't nothing. It's a state brimming with quantum potential, governed by fundamental laws. Maybe the real miracle isn't that particles emerged, but that the rules existed at all to allow them to. While quantum fluctuations in the void may sound like something ripped from the pages of science fiction, there's actual evidence etched across the sky, hidden in the faint glow of the cosmic microwave background. This ancient light, the afterglow of the Big Bang itself, carries imprints from the universe's infancy, like fingerprints left behind by those first particles. And what scientists have found is astonishing tiny variations in temperature, patches where the early universe was ever so slightly denser or hotter than average. These imperfections aren't random noise, they match precisely what you'd expect if quantum fluctuations stretched across the cosmos during its explosive expansion. Think of it like looking at a frozen pond on a winter morning. The cracks and ridges in the ice didn't form by accident, they're clues to the forces that shaped it as the water froze. In the same way, those subtle hot and cold spots in the cosmic microwave background are cosmic hieroglyphs, telling the story of how microscopic quantum jitters ballooned into the vast structures we see today. Telescopes like Planck and WMAP have mapped these patterns with incredible precision, and the data aligns eerily well with predictions made by quantum field theory. It's as if the universe left us a message in code, and we're finally starting to crack it. But here's where things get even wilder. Some of these fluctuations appear to be locked in, at scales far larger than any quantum process should allow, like finding a single ripple that somehow stretched across an entire ocean. This has led to bold new ideas like cosmic inflation, where the universe underwent a sudden, exponential expansion in its first fraction of a second. Imagine blowing up a balloon so fast that tiny wrinkles on its surface become continent-sized folds. If inflation happened, it would explain why those primordial quantum ripples left such colossal marks on the cosmos. Of course, not every scientist is convinced. Skeptics point out that while the cosmic microwave background supports the general idea of early fluctuations, it doesn't prove they originated from a quantum vacuum. Alternative explanations, like exotic fields or undiscovered physics, could also account for the patterns we see. Yet the elegance of the quantum fluctuation hypothesis is hard to ignore. It ties together two of the most successful theories in physics, quantum mechanics and general relativity, in a way that feels almost inevitable. What's truly remarkable is how far we've come in deciphering these cosmic breadcrumbs. Less than a century ago, we didn't even know the universe had a beginning. Now we're reconstructing events so brief they make a snap of the fingers seem eternal. And with next-generation telescopes poised to study the cosmic microwave background in even greater detail, we might be on the verge of an even deeper revelation, one that takes us closer than ever to answering the ultimate question: how did something as vast and complex as our universe emerge from what appears to be nothing at all? What if the universe didn't just expand, it exploded outward faster than the speed of light in a sudden, unimaginable burst? This is the radical idea at the heart of the Inflationary Universe Model, a theory that reshaped our understanding of cosmic origins. Picture this: in the first trillionth of a second after the Big Bang, space itself underwent a growth spurt so violent, it would make today's expanding universe seem sluggish by comparison. Physicist Alan Guth proposed this idea in the early 1980s, and it wasn't just a tweak to existing cosmology, it was a revolution. Inflation solves two of the biggest mysteries in physics with one elegant mechanism. First, the horizon problem. Why does the cosmic microwave background look so eerily uniform in all directions, as if distant regions of space were once close enough to exchange heat? Without inflation, these regions would never have had time to reach equilibrium. But if space expanded exponentially faster than light could travel, it would have stretched a tiny, homogeneous patch into the vast cosmos we see today. Second, the flatness problem. Why is the universe's geometry so perfectly balanced between expansion and collapse? Inflation flattens the cosmos like a balloon's surface, smoothing out as it inflates. But here's where it gets even more fascinating. This runaway expansion wouldn't just stretch space, it would also stretch the quantum fluctuations we talked about earlier, amplifying them from subatomic tremors into the seeds of galaxies. Think of it like rolling dough studded with microscopic raisins. As the dough inflates, the raisins don't just spread apart, they become the blueprint for where galaxies will eventually form. Inflation transforms randomness into structure, turning quantum whispers into cosmic shouts. Critics initially dismissed Guth's idea as too speculative, but the evidence has piled up. The cosmic microwave background's temperature variations match inflation's predictions with stunning precision, and the theory elegantly explains why we don't see exotic relics like magnetic monopoles that have been diluted to near non-existence by inflation's relentless stretch. Yet mysteries remain. What triggered inflation? What stopped it? Some theorists propose a hypothetical field called the inflaton, whose energy drove the expansion before decaying into the particles we know today. Others suggest inflation wasn't a one-time event but part of a cyclical process, a cosmic inhale and exhale across eternity. The implications are profound. If inflation is true, our observable universe might be just one bubble in an endless froth of inflating regions, each with its own laws of physics. It's a humbling thought. The particles we take for granted might simply be the ones that survived the universe's most extreme tantrum. And as experiments like BICEP study the polarization of ancient light for telltale signs of gravitational waves from inflation, we might soon know whether this breathtaking idea is really how it all began. Gravitational waves are often called the universe's echo, ripples in the fabric of spacetime itself generated by the most violent cosmic events. But what if some of these waves aren't just echoes of colliding black holes or neutron stars? What if they're whispers from the universe's very first moments carrying secrets about inflation? This is the tantalizing possibility that has physicists racing to detect primordial gravitational waves, the elusive fingerprints of the Big Bang's explosive infancy. The connection between inflation and gravitational waves is both subtle and profound. According to inflationary theory, the rapid stretching of space wouldn't just amplify quantum fluctuations, it would also send shockwaves through spacetime itself. Picture a drum struck with unimaginable force. The vibrations would ripple outward, distorting everything in their path. In the same way, inflation would have generated gravitational waves with unique signatures, imprinting them onto the cosmic microwave background like a watermark on ancient parchment. This is where experiments like BICEP come in. Nestled in the pristine darkness of the South Pole, the BICEP array scans the sky for a specific pattern in the cosmic microwave background's polarization, a faint swirled signature known as B mode. These twisted patterns could be the smoking gun of primordial gravitational waves, evidence that spacetime itself trembled during inflation. In 2014, the BICEP team made headlines with a tantalizing detection, but the signal turned out to be partly contaminated by interstellar dust. Yet the hunt continues with next-generation instruments like BICEP Array and the Simons Observatory pushing sensitivity to unprecedented levels. Why does this matter so much? Detecting these waves would be like finding a fossilized footprint of the Big Bang's first moments. Unlike light, which scatters off matter, gravitational waves travel almost undisturbed, carrying pristine information from an era before atoms even existed. Their strength would tell us how energetic inflation truly was, whether it was a gentle puff or a cataclysmic jolt, and their frequency could reveal whether inflation lasted a fraction of a second or far longer, reshaping our timeline of cosmic history. But there's a twist. Not all gravitational waves are created equal. Some theorists argue that alternative models like bouncing cosmologies or colliding brane universes could produce similar signals. Others point out that quantum effects during inflation might have generated waves too faint for current telescopes to spot. This uncertainty fuels a vibrant debate. Are we on the verge of confirming inflation, or could nature have fooled us with a cosmic red herring? The stakes couldn't be higher. If primordial gravitational waves are found, they'd rank among the greatest discoveries in cosmology, placing inflation alongside relativity and quantum mechanics as pillars of modern physics. But if they remain elusive, it might force us to rethink whether inflation happened at all, or whether the universe's birth was even stranger than we've dared to imagine. Either way, the search itself is a testament to human curiosity, pushing telescopes to their limits in the quest to read the universe's oldest story, written not in ink or stone, but in the trembling fabric of reality. String theory rewrites the cosmic rulebook with a startling idea. What if the fundamental particles we've been studying for decades aren't particles at all? Instead, picture unimaginably tiny threads of energy vibrating like the strings of a cosmic guitar. Each note they play corresponds to a different particle and electron, a quark, even the elusive graviton. This elegant symphony of vibrations could be the hidden language of the universe, a single framework that finally reconciles quantum mechanics and Einstein's general relativity. For centuries, physicists have struggled to unite these two pillars of modern physics. Quantum mechanics governs the microscopic world with bizarre probabilities and uncertainty, while relativity sculpts spacetime on cosmic scales. The problem: they speak entirely different mathematical languages, clashing violently when forced to describe the universe's earliest moments. String theory cuts through this stalemate with a radical shift in perspective. Instead of treating particles as dimensionless points, it imagines them as one-dimensional strings, so small that a single atom would dwarf them by a factor of 100 billion. At these scales, the distinction between particle and wave blurs. What we perceive as matter becomes the harmonics of vibrating strands. The implications are staggering. Take gravity, for example. In traditional quantum field theory, gravity's force-carrying particle, the graviton, introduces nightmarish infinities. But in string theory, gravitons emerge naturally as a specific vibrational mode of closed strings, like a particular chord resonating from a plucked loop. Even more remarkably, the mathematics of vibrating strings inherently describes curved spacetime, bridging the gap to Einstein's equations without brute force stitching. It's as if the universe's two great theories were always fragments of a deeper, unified melody, but strings demand a dramatic reimagining of reality. To make the equations work, they require extra spatial dimensions, not just the 3 we experience, but 6 or 7 more, curled into shapes called Calabi-Yau manifolds. Picture a garden hose seen from a distance. It looks one-dimensional until you zoom in and notice its circular cross-section. Similarly, these hidden dimensions might be compactified, detectable only through their influence on particle properties. Some theorists speculate that variations in these shapes could explain why we observe exactly 3 generations of quarks or the precise strength of electromagnetic forces. Critics argue string theory's lack of experimental verification makes it more philosophy than physics. Without technology to probe the Planck scale, 10 to the negative 35 meters strings remain tantalizingly out of reach. Yet supporters counter that the theory's mathematical consistency is itself evidence. After all, general relativity was once untested, its equations deemed too beautiful not to reflect reality. And while strings may seem exotic, their vibrational patterns elegantly replicate the entire known particle zoo, from photons to Higgs bosons. Perhaps most provocatively, string theory suggests the first particles weren't particles at all. They were the strings themselves, vibrating in the searing heat of the early universe. As spacetime cooled, their harmonics froze into the diverse matter and forces we recognize today. This transforms the Big Bang from a singular explosion into a dynamic rearrangement of cosmic strings, a shift in vibrational modes across the fabric of reality. It's a vision where the universe's birth wasn't just about energy condensing into matter, but about the very rules of physics tuning themselves into existence, one vibrating string at a time. But what if the strings of string theory are dancing in more dimensions than we can see? The idea that our universe might have hidden, compactified dimensions sounds like pure science fiction, yet it's a mathematical necessity for string theory to work. These extra dimensions aren't sprawling, expansive directions like left, right, or up, down. Instead, they're curled up so tightly they'd be invisible even to the most powerful microscopes. Imagine an ant crawling along a telephone wire. From a distance, the wire looks one-dimensional, but up close, the ant can move in a tiny circular dimension around the wire's surface. In the same way, every point in our familiar three-dimensional space might harbor 6 or 7 additional dimensions, folded into intricate shapes called Calabi-Yau manifolds. These extra dimensions aren't just mathematical curiosities, they could hold the key to why particles behave the way they do. The way a string vibrates depends on the geometry of the space it's moving through, much like how a guitar string's tone changes if you press it against different frets. So, if early particles were really vibrating strings, their properties, mass, charge, even the forces they feel, would be determined by how these strings interact with the hidden dimensions. A slight twist in the shape of a Calabi-Yau manifold could mean the difference between an electron and a quark, or between electromagnetism and the strong nuclear force. This raises a tantalizing possibility. The universe's first particles might not have been fixed entities at all, but flexible vibrations shaped by the topology of higher dimensions. In the extreme heat of the Big Bang, before these extra dimensions stabilized, strings could have flickered between different vibrational states, creating a chaotic soup of protoparticles with fleeting properties. It's only as the cosmos cooled that the extra dimensions settled into their current configuration, locking strings into the stable harmonics we recognize as electrons, photons, and neutrinos today. Some theorists take this even further, suggesting that gravity, the weakest of the fundamental forces, might appear feeble only because it's leaking into these extra dimensions. While other forces are confined to our familiar three-dimensional brain, gravity could be spreading its influence across the full multidimensional landscape, diluting its strength in our observable universe. If true, this would explain why gravity is so absurdly weak compared to, say, electromagnetism. An electron's electric force can overpower the gravitational pull of an entire planet. Of course, not everyone is convinced. Skeptics argue that without experimental proof, extra dimensions remain speculative. But recent work in particle physics and cosmology offers intriguing hints. The Large Hadron Collider has searched for microscopic black holes that might form if extra dimensions exist, while precision measurements of gravity at submillimeter scales could reveal deviations from Newton's inverse square law, a telltale sign of hidden dimensions. So far, the evidence hasn't materialized, but the search is far from over. What's fascinating is how this idea reframes the birth of the universe. Instead of a simple expansion of three-dimensional space, the Big Bang might have been a multidimensional event, with extra dimensions unfurling or compactifying as the cosmos cooled. The particles we take for granted could be cosmic fossils, their properties frozen by the way higher dimensional geometry crystallized in those first moments. It's a vision of creation where the fabric of reality isn't just stretched, it's intricately folded, with every fold whispering secrets about how the universe chose its rules. And if we're ever able to detect these hidden dimensions, it wouldn't just confirm string theory, it would rewrite our understanding of what matter, energy, and even space itself truly are. What if space-time itself is woven from threads, not smooth and continuous like Einstein imagined, but stitched together from tiny, indivisible loops? This electrifying possibility lies at the heart of loop quantum gravity, a rival to string theory that dares to rewrite the rules of reality. Forget particles floating in space here. Space itself is built from a dynamic web of intersecting loops called spin networks, each carrying quantized units of area and volume. Picture a cosmic tapestry where every thread represents a fundamental grain of spacetime, vibrating with energy. In this radical framework, the universe's first particles wouldn't have emerged within space, they'd have been born from the fabric of space. As these spin networks evolved in the early universe's extreme conditions, their intersections could have concentrated energy into localized knots, creating what we now perceive as particles. It's like watching a knitter's needles transform loose yarn into patterns, except here, the yarn is pure geometry, and the stitches are quantum jumps in spacetime itself. The math behind this is both beautiful and mind-bending. Each loop in the network carries a spin value analogous to how particles have quantum spin. When loops intersect, their spins combine in precise ways, generating discrete units of area. Imagine pixels on a screen, but for the cosmos. This granularity solves a notorious problem in physics, the infinite densities predicted by classical black holes and the Big Bang. In loop quantum gravity, nothing can shrink beyond the smallest possible volume, preventing singularities by nature's own quantum stitching. But how exactly could these abstract loops spawn familiar particles? Some models suggest that specific configurations of excited spin networks could mimic particle properties. An electron, for instance, might arise from a particularly twisted knot in the spacetime fabric, its mass and charge determined by how surrounding loops interact. Even more strikingly, the theory predicts that spacetime's quantum structure could create particle-like excitations without requiring pre-existing matter fields. The universe might have bootstrapped its own contents from pure geometry. Critics point out that loop quantum gravity hasn't yet reproduced the full particle spectrum of the Standard Model, unlike string theory's prolific vibrational modes. Yet proponents argue its minimalist approach, no extra dimensions, no unseen strings, makes it more elegant. Recent work even suggests spin networks could explain dark matter, with certain loop configurations behaving like invisible massive particles. And unlike string theory's elusive strings, some aspects of loop quantum gravity might be testable through subtle spacetime graininess in high-energy cosmic rays. The implications are staggering. If spin networks are real, the Big Bang wasn't just the birth of matter, it was the crystallization of spacetime's architecture, a phased transition where abstract quantum loops first knit themselves into the universe we recognize. Particles wouldn't be inhabitants of space, they'd be expressions of it, like whirlpools in a rushing river. This turns the very notion of empty space on its head. What we call a vacuum might be a seething ocean of spin network activity, with particles merely its most noticeable ripples. Perhaps most poetically, loop quantum gravity suggests that time itself emerges from the spin network's evolution. There's no external clock ticking. Change is just the network reconfiguring moment by moment. In this view, the first particles weren't forged in time. They helped create time as the cosmic tapestry began weaving its own history. It's a vision that blurs the line between container and contained, asking us to consider that the universe's deepest truth might not be about what exists in space, but what space itself truly is. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cycle of cosmic rebirth? The Big Bounce hypothesis takes loop quantum gravity's spin networks and weaves them into a breathtaking narrative where universes don't die, they recycle. Picture this: instead of a singular explosion from nothing, our universe could have sprung forth from the collapsing remains of a previous cosmos, its particles and laws reshuffled in the process like a deck of cards tossed into a cosmic whirlwind. At the heart of this idea is the quantum nature of spacetime itself. In loop quantum gravity, spin networks prevent the infinite crushing density of a singularity, the infamous endpoint of black holes and the classical Big Bang. Instead, as a collapsing universe reaches its smallest possible volume, these quantum loops resist further compression, creating an elastic rebound effect. Think of it like squeezing a spring to its limit. Push too hard and it snaps back with equal force. In this case, the spring is space-time, and the snapback is a new universe bursting forth from the ashes of the old. But how would particles survive such an apocalyptic transition? Here's where spin networks reveal their genius. As the previous universe contracted, its energy wouldn't vanish, it would be encoded in the evolving geometry of the loops. Matter and forces might dissolve into pure geometric excitations, only to re-emerge in the rebound as spacetime's fabric vibrated anew. It's akin to melting down a sculpture and recasting it into a fresh form. The material remains, but its structure transforms. Some theories suggest this could explain quirks like the universe's matter-antimatter asymmetry. Each bounce might slightly alter physical laws, leaving traces of prior cycles in the physics we observe today. The implications are profound. If the Big Bounce is real, the first particles of our universe weren't truly first at all. They were refugees from a prior cosmic epoch, reshaped by the violent transition. This casts familiar entities like electrons or quarks in a startling new light. They might carry echoes of ancestral universes in their quantum properties, hidden signatures of a history stretching back further than time itself. Even the vacuum of space could retain a faint memory of earlier phases, like ripples lingering on a pond long after the stone's splash. Critics highlight challenges, of course. Without observational evidence tying our universe to a predecessor, the Big Bounce risks becoming metaphysical speculation, yet tantalizing clues exist. The cosmic microwave background's uniformity, often cited as evidence for inflation, could also reflect the pre-bounce universe's prolonged contraction, smoothing out irregularities. And if primordial gravitational waves are ever detected with specific frequency patterns, they might reveal the imprint of a pre-Big Bang collapse. Supporters counter that the theory's elegance lies in its continuity. Unlike models requiring a singularity, a mathematical breaking point where physics fails, the Big Bounce offers a seamless transition governed by quantum geometry. It's a universe that refuses to die, transforming catastrophe into creation with every cycle. Perhaps most mesmerizing is the philosophical shift this inspires. If universes bounce eternally, then particles aren't just inhabitants of space-time, they're transient expressions of an immortal cosmic rhythm, fleeting notes in an infinite symphony of collapse and renewal. The atoms in your body might have danced through countless previous universes, their quantum spins whispering secrets from eons we can scarcely imagine. And when our cosmos meets its eventual fate, those same particles could ride the spin networks into another dawn, ready to begin the story anew. Imagine holding a snow globe, except instead of a tiny scene inside, the entire three-dimensional world you see is actually a perfect illusion, projected from information etched onto its curved surface. This is the essence of the holographic principle, one of the most radical theories in modern physics. It suggests that particles, everything from the electrons in your body to distant stars, might not be truly three-dimensional objects at all. They could be shadows, projections of data encoded on a distant cosmic boundary, like a movie playing on the universe's ultimate screen. The idea didn't emerge from pure speculation, but from the paradoxical behavior of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume as you'd expect, but to its surface area. It's as if all the data about what fell into the black hole wasn't stored inside but smeared across its event horizon, the point of no return. Later, Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might operate the same way. Here's how it could work. Picture the universe as a vast cosmic theater, where the stage isn't the three-dimensional space we perceive, but a two-dimensional surface at its edge. Perhaps the inflationary horizon from the Big Bang's first moments. Every particle interaction, every burst of light, every whisper of gravity we experience in 3D space would then be a holographic projection of quantum bits, or qubits, vibrating on that distant surface. It's like watching a 3D movie through special glasses, except the glasses are the laws of physics, and the screen is the edge of reality itself. This reshapes how we think about the universe's first particles. If the holographic principle holds, those primordial entities weren't independent objects floating in space. They were pixels in a cosmic code, their properties determined by how information was scrambled or entangled on the boundary. A quark's mass or a photon's energy wouldn't be intrinsic qualities but emergent ones, like the apparent depth in a hologram that vanishes when you tilt the card. Even spacetime itself might be a derived concept woven into existence by the way these boundary qubits interact. Critics argue that without experimental proof, the holographic principle remains a compelling metaphor rather than established physics. Yet tantalizing hints emerge from unexpected places. String theorists have found mathematical equivalences between descriptions of certain higher dimensional spaces and their lower dimensional boundaries, a duality called AD/CFT correspondence. It's not direct evidence, but it shows that holography isn't just philosophical musing. It's a framework that solves concrete problems in quantum gravity. The implications are staggering. If particles are projections, then the Big Bang wasn't just the birth of matter. It was the moment the universe's projector flickered on, translating a flat, information-rich surface into the rich three-dimensional cosmos we inhabit. It's a vision that blurs the line between reality and illusion, suggesting that the deepest truths of existence might not lie in the particles we see, but in the hidden code from which they emerge. And if we could ever decipher that code, we might find that the universe's first particles were never really particles at all, just the opening notes of a cosmic symphony played on the holographic strings of spacetime. Black holes, those cosmic vacuum cleaners of infinite density, might seem like the last place to look for clues about the universe's birth, but beneath their terrifying exteriors lies a hidden order, a set of rules so precise they've rewritten our understanding of entropy, information, and even the nature of reality itself. It all starts with a deceptively simple question: what happens to the stuff that falls into a black hole? According to Einstein's general relativity, it's crushed into oblivion at the singularity. But quantum mechanics insists that information can never truly be destroyed. This paradox, the black hole information problem, led to a revolution in physics, one that connects these cosmic behemoths directly to the universe's first moments. The breakthrough came when Stephen Hawking discovered that black holes aren't entirely black. They emit a faint glow, now called Hawking radiation, slowly leaking energy until they evaporate entirely. This raised a nightmarish possibility. If a black hole vanishes, what happens to all the information about the stars, planets, or astronauts it swallowed? Theoretically, that information would be lost forever, violating quantum mechanics' sacred principle of unitarity, which states that information must always be preserved. To resolve this, physicists turned to thermodynamics, the science of heat and entropy, and found something astonishing. Black holes behave like thermal objects, with temperature and entropy proportional to their surface area, not their volume. It's as if every bit of information that falls into a black hole gets smeared across its event horizon like cosmic graffiti, preserved in 2 dimensions rather than 3. This discovery dovetailed eerily with the holographic principle we discussed earlier. If a black hole's entropy depends on its surface area, maybe the entire universe operates the same way, a 3D projection of data encoded on a distant 2D boundary. But here's where it gets even wilder. Some theorists suggest that this holographic encoding isn't just a feature of black holes, it's a relic from the universe's infancy. During the Big Bang, the entire cosmos might have been compressed into a state so dense that quantum gravity effects dominated, creating conditions eerily similar to a black hole's interior. In those chaotic first moments, the universe could have been a seething hologram, with particles emerging not as independent entities but as excitations of a deeper, boundary-bound code. Support for this idea comes from an unexpected place, the cosmic microwave background. Just as a black hole's event horizon encodes information about its contents, the inflationary horizon, the furthest light we can see from the Big Bang might hold a similar imprint. The patterns in that ancient light could be the universe's way of remembering its holographic origins, like shadows cast by a higher dimensional truth. Some models even propose that the universe's initial low entropy state, a mystery that has puzzled cosmologists for decades, could be explained if the Big Bang was a holographic reset, with information carefully arranged on a new boundary. Not everyone is convinced, of course. Skeptics argue that without direct evidence linking black hole thermodynamics to the early universe, the connection remains speculative. But the math is undeniably elegant, weaving together gravity, quantum mechanics, and information theory into a single tapestry. And as experiments like gravitational wave detectors and quantum simulators probe these extreme regimes, we might soon find clues etched in spacetime itself. Hints that the universe's first particles weren't just inhabitants of space, but fragments of a cosmic memory, written in the language of black holes and holograms. What's truly breathtaking is how this ties the unimaginably large to the infinitesimally small. Black holes, those destroyers of worlds, might hold the key to understanding creation itself. Their event horizons, gates to nowhere, could be mirrors reflecting the universe's deepest secrets, showing us that reality, at its core, might be far stranger and more interconnected than we ever dreamed. And if that's true, then every particle in existence, from the quarks in your fingertips to the light from distant galaxies, might just be notes in a cosmic melody played on the holographic strings of spacetime. Hidden in the equations of particle physics lies a profound symmetry so elegant it could rewrite the story of cosmic origins. Supersymmetry, often called SUSY, proposes that every known particle has a mysterious twin, a shadow partner we've yet to detect. These hypothetical twins aren't just minor variations, they're fundamental counterparts, balancing the cosmic books in a way that solves some of physics' biggest puzzles. And if SUSY is real, these shadow particles might have been the universe's first dominant inhabitants, shaping everything that came after. At its core, supersymmetry bridges the two great families of particles, fermions like electrons and quarks, which make up matter, and bosons like photons and gluons, which carry forces. SUSY suggests that for every fermion, there's a bosonic partner and vice versa. An electron's partner would be the selectron, a squark would partner with a quark, and even gravity's hypothetical particle, the graviton, would have a fermionic twin called the gravitino. This symmetry isn't just mathematical beauty, it could explain why gravity is so weak compared to other forces, stabilize the Higgs boson's mass, and even account for the universe's invisible dark matter. Picture the early universe as a crowded ballroom where particles waltzed in perfect pairs. In those first searing moments after the Big Bang, energy was so intense that ordinary particles and their SUSY twins would have been indistinguishable, constantly transforming into one another like dancers swapping costumes. As the cosmos expanded and cooled, this symmetry would have broken, causing the partner particles to gain enormous masses and fade from view. Some might have decayed into the particles we know today, while others, like the lightest supersymmetric particle, could have survived as dark matter, invisible but omnipresent. The implications are staggering. If SUSY particles once dominated, they could have dictated how matter clumped into galaxies, why the universe's expansion accelerates, and even why we're made of matter rather than antimatter. Experiments like the Large Hadron Collider have hunted for these elusive partners, hoping to spot telltale energy imbalances or unexpected decays. So far, the evidence hasn't materialized, pushing SUSY particles to ever higher masses, but that doesn't mean they're not there. Some theorists argue we've barely scratched the surface of possible energies, while others propose subtler versions of SUSY where particles hide in extra dimensions or decay almost instantly. What's mesmerizing is how this idea reframes creation. The particles we consider fundamental quarks, electrons, neutrinos might just be the survivors of a richer, more symmetrical reality, relics of a time when every particle had its mirror. Sussy whispers that the universe's first moments weren't chaotic but meticulously balanced, with every force and particle paired in a cosmic dance we're only beginning to understand. And if we ever detect these shadow twins, it wouldn't just confirm a theory, it would unveil a lost chapter of cosmic history, one where the universe was twice as complex and twice as beautiful as we ever imagined. Deep beneath the French-Swiss border, the Large Hadron Collider hums with activity, its 27-kilometer ring serving as the ultimate time machine. This colossal machine doesn't just smash protons, it recreates conditions unseen since the universe's first trillionth of a second, hunting for shadows of supersymmetry in the debris. Every collision is a miniature Big Bang spraying particles at near light speed, while detectors the size of apartment buildings capture their fleeting signatures. The goal, to catch a glimpse of a selectron, a squark, or even the elusive gravitino particles that, if found, would rewrite the cosmic rulebook. The strategy is simple in principle, fiendishly complex in execution. When protons collide, their energy briefly condenses into new particles, some of which might be Sussy twins. Since these hypothetical particles would be heavy and unstable, they decay almost instantly into lighter, detectable particles, but with a telltale missing energy signature. Imagine a fireworks display where some sparks vanish mid-air. That missing light hints at something invisible passing through. Similarly, when the LHC's detectors measure collisions and find energy unaccounted for, it could signal a Sussy particle escaping undetected, like a cosmic ghost slipping through the cracks. So far, the hunt has been tantalizing but inconclusive. After the Higgs-boson's discovery in 2012, hopes were high that Sussy partners would emerge next. Yet as the LHC pushed to higher energies, first at 8 trillion electron volts, then 13, no definitive supersymmetric signals appeared. Skeptics began whispering that Sussy might be a beautiful idea with no connection to reality. But supporters counter that we've barely scratched the surface. The parameter space for Sussy is vast, with some particles potentially so heavy they'd require collisions at energies far beyond the LHC's current reach. Others might decay so quickly they leave almost no trace, or could be hiding in subtle decay channels overshadowed by more mundane physics. The stakes couldn't be higher. Discovering Sussy wouldn't just confirm a theory, it would solve multiple cosmic riddles at once. Take dark matter, for example. The lightest Sussy particle, often called the neutralino, is a prime candidate for this invisible stuff that outweighs normal matter 5 to 1. Unlike other dark matter theories, Sussy provides a natural mechanism for these particles to survive from the early universe to today. Then there's the Higgs mass puzzle. Without Sussy, quantum corrections should make the Higgs impossibly heavy, yet it's surprisingly lightweight. Sussy symmetry cancels out these corrections like a cosmic accountant balancing the books, offering an elegant solution. Even if Sussy particles remain elusive, their absence speaks volumes. A null result forces physicists to rethink some of their most cherished assumptions, from the hierarchy problem to grand unification. It's a reminder that nature isn't obliged to conform to our aesthetic preferences, no matter how mathematically elegant they may be. Future upgrades, like the high-luminosity LHC set for 2029, will sift through collisions with even finer precision, while proposals for a next-generation collider with energies up to 100 trillion electron volts could finally push into Sussy predicted hiding spots. What's fascinating is how this search mirrors the universe's own evolution. Just as the LHC's collisions recreate primordial chaos, Sussy particles themselves might have once dominated the cosmos before fading into obscurity. Their discovery would be like finding the fossilized bones of a cosmic titan, a relic from when the universe was young, hot, and perfectly symmetrical. And if they're out there waiting in the data, we might soon uncover a hidden layer of reality, one where every particle we know is just half of a grander, more beautiful story. Long before atoms or even protons and neutrons existed, the universe was a seething ocean of pure energy, a roiling, chaotic broth known as quark-gluon plasma. Picture a state so extreme that the fundamental forces we take for granted hadn't yet settled into their familiar forms. In those first microseconds after the Big Bang, temperatures soared above 2 trillion degrees Celsius, so hot that even the strongest glue in nature, the force binding atomic nuclei, was powerless. Quarks and gluons, the building blocks of protons and neutrons, raced freely through this primordial soup, unshackled by the bonds that would later define matter as we know it. This wasn't just a hotter version of today's universe, it was a different phase of reality entirely, like steam compared to ice. Under normal conditions, quarks are forever confined within particles by the strong nuclear force, a phenomenon called color confinement. But in the quark-gluon plasma, energy overwhelmed this force, melting protons and neutrons back into their constituent parts. The result, a nearly frictionless fluid with near-perfect liquidity, so bizarre that scientists liken it to a cosmic mirror reflecting the universe's earliest, most violent moments. The transition from this plasma to the particles we recognize is one of the most pivotal events in cosmic history. As the universe expanded and cooled, temperatures dipped below 2 trillion degrees, allowing quarks and gluons to finally freeze out into hadrons, particles like protons and neutrons. It's akin to water vapor condensing into droplets, except here, the droplets were the seeds of all matter. The math behind this phase change is so complex it requires supercomputers to simulate, but experiments at facilities like the relativistic heavy ion collider have recreated tiny droplets of quark-gluon plasma by smashing gold nuclei at near light speed. The results are astonishing, fleeting fireballs that behave less like gas and more like a perfect liquid, with collective movements suggesting quarks and gluons interacted far more strongly than expected. What's mesmerizing is how this chaotic soup birthed the universe's structure. Tiny density fluctuations in the plasma, echoes of quantum, ripples from inflation determined where matter would eventually clump into galaxies. Had the cooling happened slightly faster or slower, the quark combinations might have favored strange matter over ordinary protons, rewriting the rules of chemistry before atoms even formed. Even more intriguing, some theories suggest traces of this primordial state might linger in neutron stars, where crushing pressures could squeeze matter back into quark soup. This phase transition wasn't just a footnote in cosmic history, it was the moment the universe chose its building blocks. Every atom in your body, every star in the sky, exists because quarks and gluons locked into place at precisely the right instant. And as colliders probe deeper into quark-gluon plasma's secrets, we're not just studying particle physics, we're glimpsing the recipe for existence itself. To witness the birth of matter itself, scientists don't need a time machine, they've built something even more extraordinary. Nestled in labs across the globe, colossal machines like the relativistic heavy ion collider and the ALICE detector at CERN are turning back the cosmic clock, recreating the quark-gluon plasma that once filled the infant universe. These aren't just experiments, they're portals to the past, forging tiny droplets of primordial soup right here on Earth. At Brookhaven National Laboratory, Rick smashes gold nuclei together at nearly the speed of light, packing so much energy into a space smaller than an atom that temperatures briefly soar past 4 trillion degrees Celsius hotter than a supernova. For less than a billionth of a trillionth of a second, the collisions melt protons and neutrons into their constituent quarks and gluons, mimicking the conditions that existed mere microseconds after the Big Bang. What emerges isn't the chaotic gas physicists expected, but a liquid so perfectly fluid it defies intuition. Measurements show this quark-gluon plasma flows with almost zero viscosity, behaving more like syrup than steam. a revelation that overturned decades of assumptions about the early universe's texture. Meanwhile, beneath the Swiss-French border, Alice takes this exploration even further. Designed as part of the Large Hadron Collider, it crashes lead ions with energies 100 times higher than Rick, creating plasma droplets that last longer and offer sharper snapshots of this exotic state. The detector's name isn't just an acronym, it's a nod to Lewis Carroll's heroine, hinting at the wonderland of quantum strangeness these experiments uncover. Alice data reveals how quarks and gluons interact when freed from confinement, showing collective movement so coordinated it suggests they were more entangled than anyone predicted, a quantum choreography written into the fabric of spacetime itself. The real magic lies in the aftermath. As these microscopic fireballs expand and cool, they recreate the universe's first particle freeze-out, letting scientists watch as quarks and gluons reassemble into hadrons, a process akin to steam condensing into water droplets but with stakes far grander. By tracking the angles and energies of thousands of resulting particles, researchers can decode the plasma's properties from its opacity to its speed of sound. One startling discovery: the quark-gluon plasma's sound waves travel at over half the speed of light, a testament to how densely packed and energetic this primordial broth truly was. Critics once argued such experiments were mere curiosities, too far removed from astrophysics to matter, but the data tells a different story. The viscosity measurements, for instance, align eerily with calculations of the early universe's behavior during the phase transition that birthed matter as we know it. Even neutron stars, cosmic remnants so dense a teaspoonful would weigh billions of tons, might harbor quark-gluon plasma in their cores, bridging lab experiments with celestial phenomena. What's emerging is a radical new picture of cosmic dawn. The early universe wasn't just a featureless inferno, it was a dynamic, turbulent sea where quarks and gluons danced to quantum rules we're only beginning to decipher. And with every collision, every droplet of recreated primordial soup, we're not just peering into the past, we're uncovering the hidden physics that set the stage for everything from the first atoms to the galaxies they eventually formed. Some of the universe's first particles might be hiding in plain sight, invisible, nearly massless, and so elusive they could permeate your body right now without a whisper of interaction. Meet actions, hypothetical particles born from a cosmic puzzle that has baffled physicists for decades. Why does the strong nuclear force which binds atomic nuclei seem perfectly balanced when it shouldn't be? In the 1970s, theorists Roberto Pexi and Helen Quinn proposed an elegant solution involving a new quantum field that subtly tweaks the strong force's behavior. But like all quantum fields, this one would have ripples, particle-like excitations dubbed actions. What started as a fix for one subatomic quirk soon revealed an astonishing possibility. These ghostly particles could be the very substance of dark matter, the mysterious invisible stuff that outweighs normal matter 5 to 1. Unlike the hulking WIMP, weakly interacting massive particles that once dominated dark matter searches, actions are feather-light, perhaps 1 trillion times less massive than an electron. Yet in the searing heat of the early universe, they could have formed in staggering numbers, condensing out of the cooling cosmos like dew on a cosmic windowpane. Their near masslessness means they'd behave more like waves than discrete particles, sloshing through galaxies in vast, coherent streams rather than clumping like ordinary matter. The hunt for actions feels like capturing whispers in a hurricane. Laboratories like the Action Dark Matter experiment use powerful magnetic fields to coax these phantoms into revealing themselves, converting them into detectable microwave photons. Others employ ultra-precise atomic clocks, watching for subtle tick rate changes as Earth moves through the galaxy's action wind. Even neutron stars might betray actions. Their intense magnetic fields could transform these particles into X-rays, leaving faint fingerprints in telescope data. What's thrilling is how actions bridge the infinitesimal and the immense. A solution to a tiny symmetry problem in particle physics could also explain the gravitational scaffolding of the entire cosmos. If they're real, actions wouldn't just be dark matter, they'd be cosmic fossils, preserving a snapshot of the universe's first trillionth of a second, when forces and particles were still choosing their identities. And unlike many exotic theories, actions require no new physics beyond the standard model's edges, making them tantalizingly plausible. The implications are cosmic in scale. If actions permeate the universe, their quantum waves might have guided galaxy formation, their subtle gravity sculpting the vast cosmic web we see today. They could even solve the missing satellite problem, the puzzling shortage of small galaxies orbiting the Milky Way, by smoothing out primordial density fluctuations with their wave-like nature. Yet skeptics point out that after decades of searching, no action signal has been definitively caught. Alternative dark matter candidates, from primordial black holes to sterile neutrinos, still vie for attention. But the action's elegance keeps drawing physicists back. It's a solution that answers too many puzzles to ignore, a single idea that could unlock both the quantum realm's secrets and the cosmos's largest structures. And if detectors ever catch their faint signal, it won't just confirm a particle, it'll reveal an invisible universe woven from threads older than atoms, lighter than light itself, holding galaxies together with whispers from the dawn of time. Imagine trying to catch a ghost with a net made of light. That's essentially the challenge facing scientists hunting for actions. At the University of Washington, the Action Dark Matter Experiment, or ADMX, has turned this cosmic sleuthing into one of the most delicate searches in physics. Inside a massive superconducting magnet chilled to near absolute zero, ADMX creates conditions where even the faintest whisper of an action could transform into a detectable microwave photon. It's like tuning a radio to a frequency no station has ever used, hoping to catch a signal from the universe's first moments. What makes ADMX so groundbreaking isn't just its sensitivity, it's the sheer creativity of its design. The experiment exploits a quirk of quantum physics. In the presence of a strong magnetic field, actions should occasionally convert into photons. ADMX's resonant cavity acts like an echo chamber for these phantom particles, amplifying any whispers into something measurable. Recent upgrades have pushed its sensitivity to unprecedented levels, scanning frequencies equivalent to action masses 1 billion times lighter than an electron. And while the detector hasn't yet struck gold, each null result tightens the net, ruling out swaths of potential action properties. But ADMX isn't alone in this quest. Across the globe, experiments like CAP in South Korea and Haystack in the U.S. are employing similar strategies with unique twists. CAP uses multiple smaller cavities to scan wider frequency ranges simultaneously, while Haystack incorporates quantum squeezing techniques, a way to cheat the limits of quantum noise to peer deeper into the action's hiding places. Meanwhile, the Baby IOXO experiment in Germany takes a different approach, aiming to detect actions streaming from the sun's core, where extreme temperatures might be manufacturing them in abundance. The stakes of these experiments are cosmic. If actions are indeed the dark matter holding galaxies together, detecting them wouldn't just solve a particle physics puzzle, it would rewrite the story of the universe's infancy. These particles would be relics of a phase transition that occurred when the cosmos was just 1 trillionth of a second old, a moment when the strong nuclear force locked into its current form. Their mass and interaction strength are directly tied to conditions in that primordial epoch, making them living fossils of quantum processes we can't recreate any other way. Yet skepticism lingers. Some theorists argue that actions might be even more elusive than current experiments can handle, perhaps interacting so weakly that they're effectively invisible to our detectors. Others propose alternative dark matter candidates, from primordial black holes to exotic quantum droplets, But the action's elegance keeps physicists hooked. It's a solution that doesn't require inventing new physics beyond the standard model's edges, just uncovering a piece we've overlooked. What's fascinating is how these experiments bridge scales. The same quantum principles that govern subatomic particles might explain the vast gravitational scaffolding of the cosmos. And if atoms or its siblings ever hear that faint action signal, it won't just be a discovery, it'll be a time capsule cracked open, revealing secrets from an era when the universe was too young for stars, too hot for atoms, but just right for forging ghosts that shape the cosmos to this day. What if our universe wasn't born from a single explosive event, but from a cosmic collision between two parallel worlds? This is the mind-bending premise of the Decode universe model, a radical alternative to the Big Bang that rewrites cosmic origins as a slow-motion crash in higher dimensional space. Imagine two immense floating sheets called brains drifting through an unseen dimension, separated by a gap smaller than an atom. According to this theory, when these brains finally collided, their impact didn't just create particles, it birthed an entire cosmos from the wreckage. The name ekpyrotic comes from the Greek word for conflagration, but this wasn't fire in any ordinary sense. Proposed by physicists Paul Steinhardt and Neil Turok, the model builds on string theory's concept of brains, multidimensional objects where particles could be trapped like dust on a tablecloth. In this scenario, our three-dimensional universe is one such brain, and the Big Bang was actually the moment another parallel brain smashed into ours, transferring energy so violently it mimicked an explosion. The resulting heat and density would have been indistinguishable from a classical Big Bang, but the origin story flips entirely. No singularity, no unfathomable starting point, just a cyclical dance of cosmic sheets in a hidden dimensional arena. What makes this idea so compelling is how it sidesteps some of the Big Bang's thorniest problems. Inflation, for instance, becomes unnecessary because the brain's slow approach would have naturally smoothed out irregularities, solving the horizon problem without rapid expansion. The cosmic microwave background's uniformity wouldn't be a mystery. It would reflect the even distribution of energy left by the brain collision. Even the universe's flat geometry emerges naturally, shaped by the brain's parallel alignment before impact. But here's where it gets truly fascinating for particle creation. In traditional Big Bang cosmology, particles emerge from cooling quantum fields. In the ekpyrotic model, they're debris from the collision itself, shards of brain material shaken loose by the crash. The first particles might have been vibrations along the brain's surfaces, string theory's loops and snippets given form by the violence of contact. Over time, these excitations would have stabilized into the quarks, electrons, and photons we recognize today. But their genesis was less a birth from nothing and more a transfer of energy between worlds. Critics highlight gaps in the theory, of course. Unlike inflation, the ekpyrotic model lacks definitive observational predictions to distinguish it from the Big Bang. And while string theory provides the mathematical backbone for brains, neither has been experimentally confirmed. Yet supporters argue that the model's cyclical nature, the idea that brains could collide, rebound, and collide again in an endless cycle, offers an elegant solution to the universe's ultimate fate. Each collision resets the cosmic clock, avoiding the heat death or big crunch of other theories. Perhaps the most poetic implication is multidimensional. If the ekpyrotic model is correct, our universe has unseen neighbors, parallel brains humming with their own particles, forces, and perhaps even life, forever separated by dimensions we can't perceive. The particles we call fundamental might just be local artifacts unique to our brain's physics after the crash. It's a humbling thought. Every atom in existence could be fallout from a higher dimensional event we'll never witness directly, a cosmic car crash whose echoes still shape reality 14 billion years later. And if future telescopes ever detect unique patterns in gravitational waves or cosmic voids, we might find evidence that our universe's origin wasn't a bang, but a collision, a single note in an infinite dimensional symphony. If the ekpyrotic universe is more than just a beautiful idea, if our cosmos truly emerged from a brain collision, then the universe should bear scars from that primordial crash. Unlike the smooth uniformity predicted by inflation, a brain collision might have imprinted unique wrinkles on spacetime itself, distortions we could detect in ancient light or gravitational waves. Think of it like examining a shattered vase for clues about how it fell. The cosmos itself could hold forensic evidence of its violent birth. One tantalizing signature lies in the cosmic microwave background's polarization patterns. When the European Space Agency's Planck satellite mapped this fossilized light with unprecedented precision, it revealed subtle swirls known as B-modes. While inflation predicts certain B-mode patterns from primordial gravitational waves, an ekpyrotic collision could leave a different fingerprint, a distinctive statistical skew in how these swirls correlate across large angular scales. It's the difference between finding a fingerprint at a crime scene and realizing the suspect was wearing gloves. The absence or alteration of expected signals can be just as telling as their presence. Gravitational wave detectors might hold even more definitive clues. The Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s, will hunt for low-frequency ripples in spacetime, the kind that could carry echoes of a brain collision. Inflationary models typically predict a smooth spectrum of gravitational waves across frequencies, but an ekpyrotic crash could produce bursts or discontinuities, like seismic waves from an earthquake rather than the steady hum of ocean waves. Some theorists even suggest that colliding brains would generate a stochastic background of gravitational waves with a unique frequency slump, a cosmic dial tone left over from the impact. Then there's the matter of cosmic strings, hypothetical one-dimensional defects in spacetime that could have formed as the brains pulled apart. These wouldn't be strings in any ordinary sense, but ultra-dense filaments of energy, thinner than an atom yet stretching across galaxies. If they exist, their gravity would subtly distort light from distant quasars, and their vibrations could emit bursts of gravitational waves detectable by future observatories. Inflation rarely produces such strings, but brain collisions almost guarantee them, making these cosmic threads a smoking gun for the ekpyrotic scenario. Critics point out that current data doesn't favor one model over the other decisively. The cosmic microwave background's patterns align broadly with both inflation and ekpyrosis, and gravitational wave astronomy is still in its infancy. But supporters argue that as measurements grow sharper, especially of the cosmic microwave background's faintest polarization signals and the gravitational wave spectrum's detailed shape, the evidence could tip decisively. The key will be finding anomalies inflation can't easily explain, like unexpected correlations between temperature fluctuations at widely separated sky positions or gravitational waves with odd frequency distributions. What's thrilling is how testable these ideas are becoming. Where once cosmology relied on theoretical elegance alone, we now have tools to probe the universe's first moments empirically. Whether through subtle twists in ancient light, whispers from gravitational waves, or the ghostly pull of cosmic strings, the ekpyrotic model's predictions are concrete enough to potentially confirm or refute it within decades. And if the evidence ever leans toward a brain collision, it wouldn't just revise our origin story, it would unveil a hidden multidimensional reality, proving that our universe is just one page in a much vaster cosmic book. Among the faintest echoes of the Big Bang, neutrinos glide through the cosmos like cosmic ghosts, nearly massless, almost invisible, yet so numerous they outnumber atoms by 1 billion to 1. These elusive particles aren't just remnants of the early universe, they're living fossils carrying secrets from a time when the cosmos was less than 1 second old. Born in the unimaginable heat of the first moments, they've streamed uninterrupted for over 13 billion years, their trajectories bent only slightly by gravity, their identities shifting as they oscillate between flavors like ethereal chameleons. What makes neutrinos so extraordinary is how they've shaped the universe while barely interacting with it. In the first second after the Big Bang, the cosmos was so dense that even these weakly interacting particles were trapped, forming a primordial neutrino soup that influenced the expansion rate and the clumping of matter. As the universe cooled, neutrinos decoupled from the rest of the plasma, flying free at nearly the speed of light. This neutrino background still permeates every cubic centimeter of space today, a relic as fundamental as the cosmic microwave background, but far harder to detect. Their fingerprints are everywhere if you know where to look. Neutrinos' near masslessness meant they streamed out of dense regions in the early universe, dragging matter with them gravitationally and smoothing out the seeds of galaxy clusters. Computer simulations show that without these particles, the cosmic web would look radically different, clumpier, with smaller voids between filaments of galaxies. Even now, neutrinos subtly tug at the largest structures in the cosmos, their collective gravity shaping the distribution of galaxy superclusters in ways telescopes are only beginning to map. Yet detecting these ancient neutrinos directly is a Herculean challenge. Unlike the cosmic microwave background's photons, which we've mapped in exquisite detail, relic neutrinos from the Big Bang have energies too low for current detectors to spot. But physicists aren't giving up. Experiments like Ptolemy aim to catch them using ultra-cold graphene sheets, where a neutrino collision could create a measurable ripple in a sea of electrons. Others hunt for indirect evidence, like subtle anomalies in the cosmic microwave background's polarization that could betray the neutrino background's presence. The stakes of this search go far beyond particle physics. If we could study these neutrino fossils, they'd offer a pristine window into the universe's first second, a time before protons formed when quarks and gluons roamed free. Their masses, still not precisely known, could reveal why our universe has more matter than antimatter, and their distribution might hint at phenomena we've yet to imagine, like phase transitions in the early cosmos that left no other trace. Critics argue that without direct detection, relic neutrinos remain theoretical phantoms, yet their influence is undeniable. From the large-scale structure of the cosmos to the delicate balance of elements forged in the Big Bang, neutrinos have quietly shaped everything. They're the universe's most pervasive witnesses, silent observers that have watched galaxies form, stars ignite, and planets coalesce, all while passing through them like whispers through a storm. And if we ever learn to listen to their stories, they might just rewrite our understanding of cosmic dawn. Buried deep beneath the Antarctic ice, the Ice Cube Neutrino Observatory isn't just a telescope, it's a time machine tuned to the universe's faintest whispers. Stretching across a cubic kilometer of crystal-clear ice, this ingenious detector doesn't look for light. It hunts for the elusive flashes created when high-energy neutrinos, those cosmic ghosts, occasionally collide with atoms in the ice. But among these rare interactions, scientists are searching for something even more extraordinary: traces of relic neutrinos from the Big Bang itself, particles that have traveled undisturbed since the first second of cosmic time. The design of Ice Cube is as bold as its mission. Over 5,000 sensitive optical sensors dangle like jewels on strings, frozen solid in the Antarctic depths. When a neutrino crashes into the ice, it generates a fleeting blue glow called Cherenkov radiation, a subatomic sonic boom moving faster than light can travel through ice. By precisely timing these faint flashes, researchers can trace the neutrino's path back to its origin, whether that's a distant supernova, a colliding black hole, or perhaps even the primordial neutrino background. It's like listening for echoes in a cathedral of ice, where every whisper might carry secrets from the dawn of creation. What makes this hunt so groundbreaking is the potential window into eras no telescope can see. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, but relic neutrinos decoupled when the cosmos was just 1 second old, a time when quarks were still condensing into protons and neutrons. If we could detect them, they'd offer an unprecedented glimpse into this violent infancy, revealing conditions far more extreme than anything we can recreate in particle colliders. The challenge: these ancient neutrinos are incredibly shy. With energies millions of times lower than their modern counterparts, they rarely interact with matter at all. IceCube's current configuration isn't sensitive enough to catch them directly, but next-generation upgrades like IceCube Gen 2 aim to change that. By adding more sensors and refining detection techniques, physicists hope to spot the telltale distortions these relic particles would create as they subtly scatter off electrons in the ice, a quantum feather brushing against the fabric of reality. Meanwhile, other projects are taking different tacks. The Ptolemy experiment plans to trap relic neutrinos using graphene sheets chilled to near absolute zero, where their minuscule impacts might nudge electrons just enough to register. Others analyze anomalies in the cosmic microwave background for indirect evidence, like faint imprints left when these ancient particles gently warped the early universe's plasma. Critics argue the odds are slim. Relic neutrino detection might require technology decades beyond our current reach. Yet every neutrino IceCube catches from distant astrophysical sources refines our models, tightening the net around their primordial cousins. And if we ever succeed, the payoff would be staggering. A direct sample of the universe's first second, a data stream carrying unfiltered truths from a time before atoms, before nuclei, when reality was a seething cauldron of pure energy. These ghostly particles could tell us why matter dominates antimatter, how the fundamental forces split apart, and whether our cosmos is just one bubble in a frothing multiverse. The pursuit embodies science at its most daring, building cathedrals of ice to catch shadows, listening for echoes older than stars, and chasing particles so ephemeral they barely exist in our reality. Yet in their silence, these cosmic ghosts might hold the loudest truths about where we all came from. Amid the familiar particles of the standard model quarks, electrons, photons, there's a haunting possibility that the universe's first building blocks weren't particles at all, at least not in any recognizable sense. Enter unparticles, a concept so strange it challenges our very definition of matter. Proposed by physicist Howard Georgi, unparticle physics dares to imagine entities that don't fit neatly into the boxes of mass, spin, or charge. Instead, these enigmatic objects behave like fragments of reality, operating in fractional dimensions with properties that blur the line between particle and wave, substance and shadow. Picture a droplet of ink dissolving in water, not dispersing evenly but forming intricate fractal patterns that defy whole numbers. Unparticles would be the cosmic equivalent, lacking definite mass or momentum, yet influencing their surroundings in measurable ways. Unlike electrons or protons, which occupy specific energy states, unparticles would exist in a kind of quantum fog, spreading across energy levels like a chord resonating at every possible frequency simultaneously. If they existed in the early universe, they wouldn't have decayed or annihilated like ordinary particles. They might have faded into the background, leaving only subtle imprints on the cosmos's structure. Where could such bizarre entities come from? The theory suggests they'd emerge from a hidden sector of reality, governed by forces we've yet to discover. At extremely high energies like those in the universe's first moments, these forces could produce unparticles through interactions with standard model particles, like a ghostly hand stirring the cosmic soup. As the universe cooled, unparticles would decouple, becoming increasingly detached from ordinary matter. Yet their influence might linger. Some models propose that unparticle-mediated forces could explain anomalies in galaxy rotation curves, offering an alternative to dark matter. Others speculate that their fractional dimensional nature might leave fingerprints in the cosmic microwave background, subtle statistical deviations from the predictions of conventional physics. The implications are dizzying. If unparticles were among the first particles to emerge, they could have shaped the universe's expansion rate or seeded density fluctuations in unexpected ways. Their presence might even resolve lingering puzzles, like why gravity is so weak compared to other forces. Unparticles could act as intermediaries, diluting gravity's strength across hidden dimensions. Unlike traditional particles, which leave clear trails in detectors, unparticles would interact so weakly that their signals would be nearly indistinguishable from noise. Yet experiments like the Large Hadron Collider are searching for their telltale missing energy signatures, while precision measurements of neutron stars and black hole mergers might reveal their gravitational whispers. Critics argue that unparticle physics strays perilously close to untestable speculation. Without direct experimental evidence, it risks becoming a mathematical curiosity rather than a description of reality. But supporters counter that the same was once said of neutrinos and the Higgs boson entities deemed too elusive to detect until technology caught up. What's certain is that unparticles force us to rethink the most basic assumptions about matter. If they're real, the universe's first building blocks weren't tidy packages of mass and energy, but something far stranger, fragments of a deeper, wilder reality, where the rules of dimensionality itself were still being written. And if future experiments ever catch a glimpse of these phantom entities, it wouldn't just add a new particle to the catalogue, it would rewrite the cosmic origin story, revealing that the infant universe was stranger, richer, and more mysterious than we ever dared to dream. Scale invariance turns traditional particle physics on its head. What if the building blocks of reality don't play by the usual rules of size and energy? In our everyday world, objects behave differently depending on scale. A grain of sand doesn't act like a boulder, and a ripple in a pond bears little resemblance to an ocean wave. But unparticles defy this expectation, acting the same whether you're observing them across atomic distances or galactic spans. It's as if the universe forgot to assign them a fixed scale, leaving them untethered from the hierarchies that govern ordinary matter. This radical idea emerges from a simple but profound observation. While known particles have definite masses and interact at specific energy scales, unparticles would operate under scale-free symmetry. Picture a fractal coastline. Zoom in or out, and the pattern remains eerily similar, with no fundamental unit defining its structure. Unparticles would exhibit this same self-similarity, manifesting as fractional fragments of reality rather than discrete, countable particles. A single unparticle event could mimic the statistical signature of multiple particles, or vice versa, blurring the line between one and many in a way that'd make quantum mechanics look straightforward. The implications ripple through cosmology. If unparticles existed in the early universe, their scale-invariant nature could have left fingerprints in the distribution of galaxies or the cosmic microwave background. Unlike conventional particles, which clump predictably under gravity, unparticles might distribute their influence in fractal-like patterns, subtly altering how matter condensed after the Big Bang. Some models suggest this could explain anomalies in large-scale structure, like why certain galaxy clusters appear more evenly spaced than standard physics predicts. Others speculate that unparticle-mediated forces might mimic dark energy's effects, offering an alternative explanation for the universe's accelerating expansion. Yet detecting these phantoms requires rethinking experimentation itself. Traditional particle detectors rely on measuring definite energies and momenta, precisely what unparticles lack. Instead, physicists hunt for missing energy in particle collisions or anomalies in scattering angles that hint at fractional dimensions. The Large Hadron Collider has scoured its data for these signatures, while precision studies of neutron stars, where extreme densities might amplify unparticle effects, could reveal their gravitational whispers. Even the periodic motion of pendulums in ultra-sensitive lab experiments might someday register the faintest tug of an unparticle force. Critics argue that without direct evidence, scale invariance remains a mathematical curiosity. Yet history shows that seemingly abstract symmetries often precede breakthroughs. Think of how gauge symmetries predicted the existence of W and Z bosons decades before their discovery. Unparticles challenge us to imagine a universe where the first building blocks weren't tidy packages of matter, but echoes of a deeper symmetry, written into the fabric of reality before time itself had a scale. And if future experiments ever catch their trace, it wouldn't just add a new particle to the catalog, it would redefine what a particle even is. Imagine a world where every magnet, no matter how many times you split it, refuses to surrender its inseparable pair of north and south poles. This isn't just reality, it's one of physics' most stubborn puzzles. Yet in 1931, the brilliant Paul Dirac dared to ask, what if single magnetic poles called monopoles actually exist? His calculations revealed a tantalizing possibility that the fundamental equations of electromagnetism wouldn't just allow for these solitary north or south poles, they'd demand them under certain conditions. The catch: no one's ever found one. Dirac's reasoning was as elegant as it was radical. Just as electric charges come in discrete positive and negative units, he proposed that magnetic charges might too. His math showed that if even a single magnetic monopole existed somewhere in the universe, it would elegantly explain why electric charge is quantized, why electrons and protons carry charges that are exact multiples of a fundamental unit. It's as if the universe whispered a secret symmetry to Dirac, one that tied electricity and magnetism together at the deepest level. But here's where cosmology cranks up the intrigue. In the unimaginable heat of the early universe, grand unified theories attempts to merge electromagnetism with the strong and weak nuclear forces predict that monopoles should have formed abundantly during a phase transition, like cracks freezing into ice. As the infant cosmos cooled, these theories suggest the unified force fractured into the distinct forces we know today, and topological defects in spacetime's structure could have crystallized as monopoles. We're talking particles so massive they'd make Higgs bosons look featherweight, carrying magnetic charges billions of times stronger than an electron's electric charge. The problem: if monopoles were forged in such numbers during the Big Bang, their sheer density today should make the universe's magnetic fields look drastically different than what we observe. This glaring mismatch, dubbed the monopole problem, became one of the key motivations for cosmic inflation, the idea that the universe underwent a brief period of exponential expansion, diluting monopoles to near invisibility. Yet inflation's solution comes with its own puzzles. If monopoles were scattered so thinly, how could we ever hope to detect one? Enter modern experiments, where physicists hunt for these relics with ingenuity bordering on obsession. Some search for monopoles in ancient mica crystals, where a passing monopole millions of years ago might have left atomic-scale scars. Others use superconducting loops, exquisitely sensitive detectors that would ring like quantum alarm bells if a monopole's intense magnetic field passed through. The most ambitious efforts repurpose particle colliders, hoping to manufacture monopoles through sheer energy, though the required energies might exceed what even the Large Hadron Collider can muster. What makes this search so compelling isn't just the chance to validate Dirac's vision, it's the cosmic domino effect a discovery would trigger. Monopoles surviving from the universe's first moments would be time capsules, preserving data about grand unification energies we can't recreate in any lab. Their properties could reveal how symmetries broke as the cosmos cooled, why we live in three spatial dimensions, even whether additional dimensions lie curled up beyond perception. And if inflation did erase most monopoles, finding even one would let us measure that inflationary epoch's duration with precision, a window into processes that shaped everything from galaxy formation to the very laws of physics. The irony is delicious. A particle predicted to explain nature's symmetries has become a touchstone for understanding how those symmetries shattered. Whether monopoles remain hidden or finally reveal themselves, their ghostly presence has already reshaped cosmology, proving that sometimes the universe's most profound truths lurk not in what we see, but in the voids left by what we've yet to find. If the grand unified theories are right, magnetic monopoles should be everywhere, floating through space like cosmic relics from the universe's fiery birth. Yet despite decades of searching, not one has ever been found. This glaring absence isn't just a minor puzzle. It's a crisis that threatened to unravel our entire understanding of cosmic origins until an audacious idea called inflation came to the rescue. At first glance, the monopole problem seems simple. If these particles formed as the universe cooled from the unimaginable temperatures of grand unification, calculations suggest we'd be swimming in them. The numbers are staggering enough monopoles to outweigh all visible matter in the cosmos, their sheer density making the universe's magnetic fields look like a tangled mess. Yet when we peer into space, we find no trace of them. It's as if someone took a cosmic eraser and scrubbed them nearly clean from existence. This is where inflation swoops in like a plot twist in a cosmic mystery. Proposed in the early 1980s by physicist Alan Guth, inflation suggests that the universe underwent a mind-bending expansion in its first trillionth of a second, not just growing but doubling in size at least 60 times over. That exponential stretch would have diluted everything from monopoles to any other defects, spreading them so thin they'd be virtually undetectable today. Imagine blowing up a balloon with a few grains of sand stuck to its surface. As the balloon inflates, those grains become so widely scattered you might never spot one by chance. Inflation does the same to monopoles, solving the problem not by preventing their creation, but by ensuring most were flung so far beyond our observable horizon they might as well be gone. But there's a fascinating catch. Inflation doesn't just sweep monopoles under the rug, it leaves clues about their existence in the fabric of space-time itself. If even a handful of monopoles survived the expansion, their gravitational influence could subtly warp the cosmic microwave background or leave faint imprints on large-scale galaxy distributions. Some models even suggest that certain patterns in primordial gravitational waves, ripples in spacetime from the early universe, might carry fingerprints of monopoles interacting with inflationary fields. The beauty of this solution lies in its elegance. Inflation doesn't just explain why we don't see monopoles, it ties their absence to broader cosmic mysteries, like why the universe is so flat and uniform on large scales. And if future experiments ever detect a single monopole, it wouldn't just confirm grand unified theories. It could help us measure inflation's exact duration and energy scale, offering a window into physics at energies we can't hope to recreate in any lab. Critics, of course, raise valid questions. If inflation diluted monopoles so effectively, why haven't we seen any trace of them at all? Shouldn't there at least be a few stragglers within our cosmic neighborhood? Others argue that alternative solutions, like monopoles being rarer than initially predicted or decaying into other particles, could explain their absence without invoking inflation. Yet despite these debates, the monopole problem remains one of inflation's strongest motivators, a smoking gun for a process that reshaped the entire cosmos before the first particles as we know them even existed. What's remarkable is how this interplay between theory and observation keeps pushing the boundaries of our understanding. The hunt for monopoles isn't just about finding a missing particle, it's about testing the very mechanisms that may have set the stage for everything that followed. And whether these elusive magnetic ghosts are ever found or remain forever hidden, their story is woven into the fabric of cosmology, reminding us that sometimes absence speaks louder than presence. Among the most peculiar residents of the supersymmetric universe is the gravitino, the hypothetical superpartner of the graviton, itself the elusive quantum carrier of gravity. Picture a particle so massive it could dwarf entire atoms, yet so weakly interacting it could pass through light years of lead without a whisper. According to supersymmetry, every force-carrying boson should have a fermionic twin, and for gravity's messenger, that twin is the gravitino. But while this particle might sound like just another entry in the roster of sussy shadow particles, it poses a cosmic paradox that could unravel our understanding of the early universe. The problem starts with their sheer abundance. In the scorching heat of the Big Bang's first moments, gravitinos would have been produced copiously, popping into existence via high-energy particle collisions like cosmic fireflies. Calculations suggest they'd have formed at rates comparable to photons, meaning the early universe should have been swarming with them. Here's the twist: gravitinos are staggeringly long-lived. With half-lives potentially exceeding the current age of the universe, these relics wouldn't decay away like other exotic particles. Instead, they'd linger, their collective mass subtly warping the cosmos's expansion and structure in ways that clash violently with observations. This isn't just a minor accounting error. If gravitinos were as plentiful as Sussy predicts, their gravitational influence would have altered the synthesis of light elements like deuterium and helium during Big Bang nucleosynthesis, the universe's first nuclear fusion reactor. The observed abundances of these elements, which match exquisitely precise theoretical predictions, leave almost no room for such meddling. Even more damning, gravitinos would distort the cosmic microwave background's temperature variations and skew the distribution of galaxies we see today. It's as if the universe left us a pristine crime scene, and gravitinos are the uninvited guests whose muddy footprints are conspicuously absent. Physicists call this the gravitino problem, and it's forced some creative solutions. One compelling fix involves tweaking the conditions of the early universe to suppress gravitino production. If supersymmetry broke at just the right energy scale, neither too high nor too low, it could have limited gravitino formation to negligible levels, like a cosmic thermostat preventing overheating. Another provocative idea suggests gravitinos might decay faster than expected through interactions with hidden sector particles, vanishing before they could wreak havoc. Some models even entertain the possibility that gravitinos, despite their fearsome mass, could be nearly weightless in certain high-energy regimes, rendering them harmless cosmic spectators. The stakes couldn't be higher. If gravitinos exist but were scarce enough to avoid these conflicts, they become prime candidates for dark matter, invisible, stable, and pervasive. Experiments like the Large Hadron Collider hunt for their signatures in missing energy events, while astrophysical probes scour gamma-ray data for hints of their decay products. Yet every null result tightens the constraints, forcing theorists to walk a razor's edge between mathematical elegance and observational reality. What makes the gravitino problem so fascinating is how it pits two pillars of modern physics against each other. Supersymmetry promises to unify nature's forces and stabilize the Higgs boson's mass, yet its own offspring threaten to undo the very cosmology it seeks to explain. Solving this riddle might require more than just tweaking parameters. It could demand a fundamental rethinking of how particles, gravity, and the universe's infancy intertwine. Whether gravitinos remain a tantalizing possibility or a fatal flaw for Sussy, their story exemplifies the delicate dance between theory and observation, where even the most beautiful ideas must ultimately face the cold, hard light of data. The gravitino problem might seem like a death knell for supersymmetry, but what if these elusive particles aren't just cosmic troublemakers? What if they're the hidden architects of dark matter itself? This tantalizing possibility flips the script entirely, transforming the gravitino from a cosmological liability into the universe's most sought-after ghost. The key lies in their decay pathways, or rather, the lack thereof. If gravitinos are stable enough to survive from the Big Bang to today, their sheer abundance could make them the invisible scaffolding holding galaxies together. Here's how it could work. In certain supersymmetric models, the lightest supersymmetric particle, often the neutralino, is a classic dark matter candidate. But gravitinos throw a wrench into this tidy picture. They're typically heavier and more weakly interacting, making them harder to produce in particle colliders or detect underground. However, if gravitinos decayed just slowly enough to persist while avoiding the overproduction that would distort cosmic history, they could strike a perfect balance. Imagine a cosmic tightrope walk: decay too fast and they vanish without a trace, too slow and they overwhelm the universe's delicate structures, the sweet spot. Lifetimes long enough to avoid early universe conflicts, yet short enough to leave behind a relic density matching dark matter observations. Experiments are already hunting for clues. Gamma-ray telescopes like Fermi scan the skies for anomalous photon bursts that could signal gravitino decays in distant galaxies. Meanwhile, the Large Hadron Collider searches for missing energy events, sudden imbalances in collision debris that might hint at gravitinos slipping undetected through the apparatus. Even precision measurements of the cosmic microwave background's polarization patterns could reveal subtle distortions caused by gravitino-induced gravitational waves during the universe's infancy. But the plot thickens when you consider alternative decay scenarios. Some theories propose that gravitinos don't decay into ordinary particles at all, but into other hidden sector particles invisible to us but equally capable of shaping the cosmos. These daughter particles might interact through unknown forces, creating intricate dark matter halos with properties that explain why galaxies rotate faster than visible matter alone can account for. Others suggest gravitinos could decay asymmetrically, producing slightly more matter than antimatter, which might solve two mysteries at once: dark matter's origin and the universe's matter-antimatter imbalance. Critics rightly point out the fine-tuning required to make this work. Gravitational interactions alone are so weak that gravitinos should barely notice ordinary matter, making it challenging to explain how they'd clump sufficiently to form dark matter's observed structures. Yet supporters counter that supersymmetry's flexibility allows for hybrid models. Perhaps gravitinos make up only a fraction of dark matter, with other particles like actions or sterile neutrinos filling the gaps. The beauty of this idea lies in its audacity. It takes a particle that once threatened to derail supersymmetry and recasts it as a potential hero, a bridge between the infinitesimal world of quantum gravity and the vast dark tapestry of the cosmos. And if future observations ever catch a whisper of gravitinos, whether in gamma-ray glimmers, collider anomalies, or gravitational wave echoes, it wouldn't just solve the gravitino problem. It would unveil a universe where the heaviest particles are also the most invisible, where dark matter isn't just an absence of light, but the lingering breath of a symmetry forged in the Big Bang's first moments. Deep in the labyrinth of cosmology's unsolved mysteries lies a peculiar idea. What if dark matter and dark energy aren't separate entities at all, but different faces of the same enigmatic substance? This is the radical proposition of the Chaplain gas model, a theory that weaves together two of the universe's greatest puzzles into a single, shifting fluid capable of shape-shifting across cosmic history. Named after Russian physicist Sergei Chaplain, this exotic medium starts its life behaving like cold dark matter, clumping together to sculpt galaxies, then seamlessly morphs into dark energy, driving the universe's accelerated expansion. It's as if the cosmos has been running on a single, dual-purpose fuel all along, its properties evolving with time like a chameleon changing colors. The mathematics behind this cosmic chameleon is as elegant as it is bizarre. Unlike ordinary gases where pressure and density follow straightforward relationships, Chaplain gas obeys a counterintuitive rule. Its pressure decreases as its density drops, creating negative pressure capable of repelling spacetime itself. Early in the universe, when matter was densely packed, this fluid would have behaved like a cold, sluggish gas, gravitating just like dark matter to seed the growth of galaxies and clusters. But as expansion diluted the cosmos, the gas's negative pressure would dominate, pushing galaxies apart with the same eerie force we attribute to dark energy. One substance, two cosmic roles, a minimalist dream for explaining the universe's biggest unknowns. But here's where it gets even wilder. Some theorists propose that this fluid didn't just shape the cosmos, it might have birthed the very particles we're made of. In certain variants of the model, the Chaplygin gas isn't perfectly uniform. Quantum fluctuations could have created dense pockets where the gas condensed into ordinary matter during phase transitions, like dew forming on a cold surface. These pockets might have become the furnaces where quarks, electrons, and eventually atoms coalesced, tying the origin of visible matter directly to the dark sector's dynamics. It's a poetic twist. The invisible scaffolding of the universe might also be the factory that produced everything we can see and touch. Of course, no groundbreaking idea escapes scrutiny. Critics point out that the Chaplygin gas struggles to explain fine details of galaxy rotation curves and large-scale structure as neatly as traditional dark matter models. Others argue that its predicted sound waves, ripples in the fluid that should affect cosmic microwave background patterns, haven't been detected with convincing clarity. Yet supporters counter that refined versions of the theory, including generalized Chaplygin gases with adjustable parameters, can match observations more closely. The debate rages on, with cosmological datasets like those from the Planck satellite and Dark Energy Survey scrutinized for hints of this elusive fluid's fingerprints. What's mesmerizing about this model is how it reframes our place in the cosmos. If correct, the atoms in your body weren't just forged in stars, they're the byproduct of a shadowy, all-pervading substance that continues to shape the universe's destiny. The same mysterious something that pulled matter into galaxies billions of years ago is now stretching space itself, accelerating us toward an uncertain future. And as astronomers peer deeper into the universe's history, measuring the tug-of-war between gravity and dark energy with ever greater precision, we might soon discover whether the cosmos runs on two fuels, or just one shape-shifting phantom quietly steering everything from the void. What if the universe's greatest mysteries, dark matter and dark energy, aren't separate puzzles at all, but two sides of the same cosmic coin? The Chaplygin gas model dares to answer this with a single, shape-shifting substance that rewrites the rules of cosmology. Picture a fluid so versatile it starts its life as clumpy, galaxy-forming dark matter before transforming into the repulsive force we call dark energy. An alchemical trick that could streamline our understanding of everything from the Big Bang's aftermath to the fate of the cosmos. At its heart, this idea challenges a fundamental assumption that dark matter's gravitational pull and dark energy's push are distinct phenomena. Instead, imagine a cosmic chameleon whose behavior depends entirely on its environment. In the early universe's crowded chaos, Chaplygin gas would have acted like cold, dark matter, its particles slow and sluggish, drawn together by gravity to sculpt the first galaxies. But as expansion stretched space thin, the same substance would shift gears, its internal pressure turning negative and pushing galaxies apart like an unstoppable cosmic tide. This metamorphosis isn't just theoretical sleight of hand. It emerges naturally from the gas's unique equation of state, where pressure and density dance in lockstep to defy everyday intuition. The implications for early universe models are profound. Most theories require finicky fine-tuning to balance dark matter's abundance with dark energy's late-game dominance. But with Chaplygin gas, these parameters unite organically. As the universe expanded, the gas's density would have inevitably crossed a critical threshold, triggering its transition from clumping to repelling. This could explain why dark energy only turned on about 5 billion years ago, not due to some abrupt cosmic switch, but as the natural consequence of a single fluid reaching its tipping point. Simulations show this unified approach can replicate large-scale structure formation just as accurately as traditional models, while elegantly sidestepping the coincidence problem. why dark energy's density happens to match dark matter's at exactly our epoch in cosmic history. Yet the real magic lies in how this model reshapes our view of primordial particle creation. Some variants propose that quantum ripples in the Chaplain fluid could have seeded not just galaxies but matter itself. Denser regions might have condensed into quark-gluon plasma during phase transitions, like droplets forming in cooling steam, meaning ordinary particles could be fossilized fluctuations in this all-pervading dark medium. It's a breathtaking synthesis. The same substance that now accelerates the universe's expansion might have once forged the atoms in your body, linking the birth of visible matter to the dark sector's hidden dynamics. Of course, no theory is bulletproof. Critics highlight tensions with precise measurements of galaxy rotation curves, where Chaplain gas struggles to replicate dark matter's detailed gravitational fingerprints. Others note that its predicted sound waves' subtle pressure oscillations imprinted on the cosmic microwave background haven't been conclusively detected. But newer, modified versions incorporating viscosity or variable sound speeds are closing these gaps. Meanwhile, upcoming telescopes like Euclid and the Vera Rubin Observatory will test key predictions by mapping how cosmic structures evolve across billions of years, a timeline where unified dark sector models make starkly different forecasts than standard cosmology. The beauty of this framework isn't just its parsimony, it's the philosophical shift it invites. If correct, we're not just inhabitants of a universe filled with mysterious dark components, we're products of their metamorphosis, riding waves in a cosmic fluid that's been reinventing itself since time began. Every galaxy, every star, every atom becomes a footnote in the biography of this enigmatic substance. A reminder that the universe's greatest secrets might not require new physics, just the courage to see familiar pieces in an entirely new light. Imagine a universe where the first particles didn't emerge from cooling plasma or quantum fields, but from the fiery depths of microscopic black holes. This is the audacious premise of the black hole genesis hypothesis, a theory that flips cosmic origins on its head. Picture the Big Bang's aftermath not as a smooth soup of particles, but as a seething froth of tiny black holes, each no larger than a proton yet hotter than a star. According to this idea, these primordial black holes weren't just cosmic roadkill. They were the universe's first particle accelerators, their explosive evaporations forging the very building blocks of reality. The math behind this is as elegant as it is mind-bending. In the early universe's extreme density, random quantum fluctuations could have packed enough matter into tiny volumes to collapse into black holes spontaneously, no dying stars required. Stephen Hawking's groundbreaking work showed that black holes aren't truly black. They radiate energy, shrinking over time until they vanish in a final burst of particles. For stellar mass black holes, this process takes longer than the current age of the universe, but for microscopic ones, they'd evaporate in fractions of a second, their deaths unleashing bursts of radiation and particles like cosmic fireworks. What makes this hypothesis so compelling is how neatly it solves multiple puzzles at once. First, the matter-antimatter imbalance. If evaporating black holes favored producing slightly more matter than antimatter, they could explain why our universe isn't just empty radiation. Second, dark matter. Certain primordial black hole mass ranges could have survived to the present day, invisible yet abundant enough to shape galaxies. Even the cosmic microwave background's smoothness might find an explanation. These black holes could have soaked up early density variations like microscopic sponges before evaporating. The real magic happens in the details. As a primordial black hole shrinks, its temperature skyrockets, reaching trillions of degrees in its final moments. At these energies, particle pairs that normally require immense colliders to create would boil off effortlessly. Quarks, gluons, even Higgs bosons might have first emerged not from cooling plasma, but from the death throes of these tiny gravitational monsters. It's a cosmic alchemy where gravity itself becomes the crucible for matter's creation. Critics point out the fine-tuning required. Primordial black holes need to form in just the right numbers and masses to match observations. Too many, and they'd overproduce dangerous radiation. Too few, and they'd be irrelevant. Yet new calculations suggest inflationary models might naturally produce the perfect distribution, with quantum ripples during inflation creating density spikes ripe for black hole formation. Others argue that evaporating black holes would leave telltale gamma-ray signatures we've yet to detect, though supporters counter that subsequent particle interactions could have scrambled these signals beyond recognition. Beyond theory, this idea reshapes how we view the universe's fabric. If correct, every atom around you might trace its lineage not to a quiet quantum fluctuation, but to the violent demise of a black hole trillions of times smaller than a grain of sand. Even space-time itself could carry scars from these fleeting gravitational pits, their brief existence warping the geometry of the early cosmos in ways we're only beginning to model. The most tantalizing possibility, some primordial black holes might still exist today, lurking in the cosmic dark. Experiments hunting for their gravitational lensing effects or final explosive evaporations could soon turn this radical hypothesis from speculation into revolutionary fact, revealing that the universe's first particles weren't born in fire, but in the ashes of vanishing black holes. Hawking radiation isn't just a slow leak from black holes. It's a torrential downpour of particles born from the violent interplay of gravity and quantum mechanics. Picture a microscopic black hole in the early universe, so small it could fit inside an atom yet packing the mass of a mountain. As it loses energy through Hawking radiation, its temperature soars to billions of degrees, transforming its surface into a particle factory of unimaginable intensity. Pairs of virtual particles, usually fated to annihilate each other instantly, are ripped apart by the black hole's gravitational grip. One falls in, while the other escapes as real radiation, a cosmic alchemy that converts gravitational energy into matter and light. But here's the twist, these aren't just any particles. At the temperatures reached during a primordial black hole's final moments, the radiation spectrum shifts from harmless photons to a fireworks display of quarks, gluons, and even Higgs bosons. It's like a particle accelerator compressed into a space smaller than a proton, running at energies far beyond anything the Large Hadron Collider could achieve. The universe's first stable matter protons, neutrons, electrons might have coalesced from this very debris, forged in the explosions of countless tiny black holes blinking out of existence. The numbers are staggering. If even a fraction of the early universe's energy density condensed into primordial black holes, their collective evaporation could have flooded space with enough radiation to rival the heat of the Big Bang itself. This deluge wouldn't have been uniform. Dense regions of black holes would have created hotspots, seeding the density fluctuations that later grew into galaxies. Some theories suggest these explosions could even explain the universe's puzzling matter-antimatter asymmetry. If black holes preferentially emitted more quarks than antiquarks, a possibility in certain quantum gravity models, their deaths might have tipped the cosmic scales toward the matter-dominated reality we see today. Yet Hawking radiation's legacy isn't just theoretical. Astronomers have scoured gamma-ray data for signs of evaporating black holes, hunting for the telltale bursts of high-energy photons that would mark their final seconds. While no confirmed detections exist, some tantalizing anomalies like unexplained gamma-ray flashes keep the hypothesis alive. Others speculate that certain ultra-high-energy cosmic rays, particles arriving from space with energies millions of times greater than anything in human-made accelerators, could be the last echoes of these ancient explosions. The beauty of this idea lies in its economy. Instead of relying on separate mechanisms for particle creation, dark matter, and cosmic structure, it bundles them into one breathtaking package. Black holes form, they shape space, they vanish, and in their dying breaths, they give birth to the very stuff of stars, planets, and life. It's a universe where destruction and creation are two sides of the same coin, where the darkest objects in existence become the engines of light. And if future telescopes ever catch the death cry of a primordial black hole, it wouldn't just confirm a theory, it would rewrite the story of how everything we know came to be. From quantum fluctuations winking particles into existence, from empty voids to colliding brains birthing entire universes in higher dimensions, we've journeyed through 30 mind-bending theories about the universe's very first particles. Some ideas emerge from equations so elegant they feel inevitable, like supersymmetry's perfect pairings or string theory's harmonious vibrations. Others thrive in the wild frontiers of speculation, where primordial black holes sculpt reality through their explosive deaths, or where unparticles dance in fractional dimensions beyond our perception. Each theory, no matter how outlandish, represents a triumph of human curiosity, a daring attempt to pry open the cosmic egg and glimpse what stirred before time itself began ticking. What's truly astonishing isn't just the diversity of these ideas, but how they intertwine. Quantum fluctuations stretched by inflation could have seeded galaxies, while actions born from symmetry puzzles might now weave through your hands as invisible dark matter. The very fabric of space-time, according to loop quantum gravity, could be stitched from spin networks that birthed particles as knots in their threads. And lurking beneath it all, the holographic principle whispers that everything we see might just be a shadow play, a 3D projection of information scrawled on the universe's distant edges. Yet for all their differences, these theories share a common thread. They force us to confront how much we don't know. Every calculation, every experiment, every observation peels back another layer, only to reveal deeper mysteries. Maybe that's the most beautiful part. Science isn't about finding final answers, but about refining the questions. The universe's first particles might remain hidden for centuries, or their secrets might crack open tomorrow in a detector's flicker or a telescope's unblinking eye. So now it's your turn. Which of these theories ignites your imagination? Do vibrating strings feel more compelling than colliding brains? Does the elegance of inflation convince you, or does the audacity of black hole genesis pull you into its gravitational sway? Drop your thoughts in the comments. Let's keep the conversation rippling outward like quantum waves in the vast ocean of the unknown. After all, the story of the cosmos isn't just written in particles and forces. It's written in the collective wonder of everyone who's ever looked up at the night sky and dared to ask how. And that includes you.